Hey guys, my name is IBM and I am going to take you into another topic which is going to be work, energy, and power. Do not forget to subscribe if you want, I don't care. These tutorials are entirely for my students. If I have a problem, they can always just watch these lessons so that they don't miss anything. So if you want to use them, it's fine. If you don't want to use them, it's always fine. But you can always watch the solved past paper questions in each of the topics I've recorded to gain more confidence. So today's topic is called work, energy, and power. That is the topic. And this topic appears to be easier when a student sees the heading work, energy, and power. And it also appears to be easier when it is taught in class, or it is going to be easier when you look at the tutorials. But when you visit the solved past paper questions, you'll understand that this is one of the hardest or the most complex or the most abstract topic. So do not forget to watch the solved past paper questions to gain more confidence. So you can go to the playlists and look for work, energy, and power. Both multiple choice questions have been solved and structured questions have been solved so that you can gain more confidence. So this is going to be lesson one. But before we explore this unit of work, energy, and power, I want you to be equipped with some concepts of dynamics and kinematics. Especially kinematics, you should have equations of motion or equations of linear motion at your fingertips. That is V equals U plus AT, S equals to a half into U plus V times T, S equals to UT plus a half AT squared, and V squared equals to 2AS. So many times we shall refer to those equations in this topic of work, energy, and power. So what do we mean by work? So the words work, energy, and power are often used in everyday English language, but of course they have a variety of meanings, which meanings we are going to explore in this unit called work, energy, and power. In our everyday life, we talk about work. I don't have energy, I don't have power, and so on and so forth. So we use it in our everyday English language, but these will be having different meanings, especially when it comes to physics. So in lesson one, we shall begin with, I think we shall cover work and power in lesson one, and then in lesson two, we shall talk about energy. I'll always start with the work and power because these are two short concepts which allows students to cover them very fast and do a lot of practice. Okay, so we are going to start with work. What do we mean by work, or what is work? So the word work in everyday life, I think, describes an activity. It describes an activity which requires something mental, or I mean an effort which could be mental, or it could be muscular, or it could be a physical effort. But of course, in physics, this is going to have a different meaning, or it's going to have a special meaning. So the word work in everyday life describes any activity which requires muscular or mental effort. Of course, when you are reading, you are doing work, but you're not using a muscular effort, but you're using a mental effort. So If you are doing work with your hands or your legs, that could be muscular effort. But if you are reading, for example, you could be doing work but not using muscular, however, it is mental effort. So in both cases, these activities are actually activities which we can call or regard to as work. However, in physics, work has a special meaning. In the scientific sense, work involves motion, according to physics, or in science in general, work involves motion, and work is done when a force changes the position or the speed of an object. So this is different from work in everyday life. If you are trying to push a wall, for example, you may think you are doing work because it is involving a muscular effort. But if it is physics or science, since the force you are applying is not changing the position or the speed of the object you are pushing, for example, pushing a wall, then we can say there is no work done. So in other words, work involves force and change in position or change in speed. And for that reason, therefore, we shall define work done as the product of the magnitude of the force applied to the body and the displacement of the body in the direction of the force or in the direction of the applied force. So work involves applying a force, and work involves a displacement of an object, and the displacement of the object is in the direction of the force. That's what we call work. The product of the magnitude of the force and the direction, the magnitude of the force and the displacement in the direction of the force. Remember, displacement is distance in a specified direction. So that is what we are going to call work. So we can write work mathematically as force times displacement in the direction of the force. So some students prefer to write work done as F times D or F times S because normally we use S for displacement rather than D for displacement. So it is extremely important for us to include direction in the definition of work done. Now some people or some students immediately ask, if we include direction, does it imply that work is a vector quantity? But I'm saying it is going to be very important for us to include direction in defining work because the force must cause a body to move in the same direction as the force. Because we may later on think of the fact that if the force acts in one direction and the work is done in the opposite direction, then the work is said to be done against. For example, if we consider friction, for example, friction tends to oppose motion. That means the work done by friction is work done against motion. That will be different. But work done is the product of force and displacement in the direction of the force. And some students will immediately think, is therefore work a scalar quantity? Think of the meaning of work before thinking about it in the scientific sense. Work in everyday life describes any activity which requires muscular or mental effort. If you're reading, in which direction are you reading? Anyway, in which direction is the mental effort? Yet a vector quantity should have direction. Anyway, we shall talk about that in more details. But if you're a mathematician, you'll notice that the product of force and displacement, these are two vectors. And the product of two vectors is always a scalar. If you're a mathematician, the product of two vectors is a scalar. So it is easier to mathematically think of the fact that work is a scalar quantity. Okay, so in IGCSE, I think you also defined work as force, product of force times displacement in the direction of the force. And it is the same thing we are talking about here. And this is what makes AS very easy. They're almost the same concepts we explored in IGCSE. However, the only thing you never explored in IGCSE is what I want to emphasize in lesson 1. So let's consider an object on which a force F is applied to cause it to move through a distance S in the direction of the force. The forces acting on this object are the weight, which acts vertically downwards, that is mg, and then the normal reaction force, which is the force from the surface vertically upwards. So let us assume this is the surface. I have to change this color meanwhile. Let's assume this is the surface. The surface exerts a normal reaction force vertically upwards. If the object is not jumping off the surface, it's only because the normal reaction force is balanced with the weight. So it's only the force F which is causing motion in this case. So can we think about the work done in this case? So since work done is the product of force times displacement in the direction of the force, if we consider such a body of mass m being pulled on a smooth surface, smooth in the sense that there is no friction, through a distance s, then the work done is going to be the force F times the displacement in the direction of the force. So I always encourage my students to use S for displacement rather than D because it is force times displacement. Later on, we shall explain why when we talk about power. So I also want you to note that if the surface is smooth, then the friction is assumed to be negligible. Of course, that is a wrong assumption because in most cases we cannot have such a surface which is smooth enough for the friction to be negligible. But every time we talk about the surface being smooth, we assume that the friction force is too small and can be ignored. So the work done is going to be force times displacement in the direction of the force. That one you mentioned in IGCSE. I want us to talk about something you never mentioned in IGCSE. We are going to consider a case when the body acts at when the force acts at an angle. So we are considering a situation where the force acts at an angle. Let's say the angle is theta to the horizontal. In the previous case, the force was acting parallel to the surface. That is what you saw in IGCSE. But to modify this or to advance, let's assume that let's consider a situation where the force acts at an angle theta to the horizontal. In that case, your concepts or ideas of resolving should now come in. If we consider such a case where force acts at an angle theta to the horizontal, then we are always going to think of a situation where the force must be acting parallel to the direction, or the force must be acting in the same direction as the displacement, or the displacement must be in the same direction as the force. So how shall we make this force to be in the same direction as the displacement? In that case, your concepts of resolving comes in here. We must take F to the horizontal. Because F is acting at an angle, so it has two components. One component is to the vertical, it has one component in the horizontal. From your concepts of scalars and vectors, where you looked at resolving, I told you that if the force, or if the vector is, if the angle is between the vector and the direction you want to resolve to, that is always cos. If you're not sure, you can still draw a right angle triangle here. You want F in the X, which is in the adjacent, but you have F in the hypotenuse. So you have adjacent over hypotenuse, that is cos. So it is as easy as saying cos of theta is the adjacent, which is Fx, over the hypotenuse, which is F, which means the part of F which acts in the horizontal is going to be F cos theta. Because the displacement is in the horizontal, we need to find F in the horizontal. That is the one which is going to do work in the direction of the displacement. Therefore, if we consider a case when the force acts at an angle theta to the horizontal, then the work done is going to be the force, the component of the force which is acting in the horizontal, that is F cos theta, then times the displacement. Of course, if you rearrange, it can also be F times S cos theta times F times S cos theta. Of course, it means we can either resolve F in the direction of S, or we resolve S in the direction of F, which is the same thing. So this means W is obtained as F. W can be obtained as force times the resolved part of the displacement in the direction of the force. W can be obtained, or the work done can be obtained by multiplying F, the force, and the resolved part of the displacement in the direction of the force, or the displacement times the resolved part of the force in the direction of the displacement. That is how we find the work done in this case. Of course, there's any other forces we could consider here for equilibrium. The component of F, therefore, which acts vertically upwards would be F sine theta. And if there is equilibrium, therefore, we can say that R, which is the normal reaction, plus F sine of theta should be the same as mg. And we can still find n of the quantities required in case we want to find them, because total forces acting upwards should be equal to total forces acting downwards. Okay, so that is the only concept you never studied in IGCSE because it required resolving, which resolving you may not have talked about or you may not have mentioned in IGCSE. That is work done. Okay, so having known how to obtain work done when the force acts at an angle, I think we are now good enough to go. So there are a few things we need to note about work done. Number one, work is only said to be done when a force moves its point of application along the direction of its line of action, or when the force acts on a body and the object or the body moves in the direction of the force. We say that the force has done work on the object. If the force does not cause the object to move, then we say that there is no work done. So if a force acts on a body and there is no motion, if a force acts and there is no motion, then there is no work done according to the scientific sense or the scientific meaning of work. For example, if you decide to push the wall of your class, you'll not be doing any work because the wall will not move. So the work done is involving you're putting in some muscular effort, but because there is no physical outcome, there is no movement of the wall, then we assume that there is no work done according to physics. Of course, the distance or displacement must be in the SI units, which are actually going to be meters. So the distance will be in SI units because the force should also be in SI units. And while work is done on a body, energy is transferred to the body, and so work can be said to be energy in transit. Without energy, the ability to do work ceases to exist. So we say that when work is being done, energy is being transferred. Therefore, sometimes we can talk about work as energy in transit, energy in motion. Some students may prefer to define work as energy in motion. Of course, that will be just the physical meaning of work. Of course, to not be the scientific definition. But with energy, we expect an object to be able to perform work. So there is transfer of energy whenever work is being done. So we can say work is energy in transit, or work done is energy in motion. So we need to note those concepts very well. Work done can be considered to be energy in transit, energy in motion, because during work, when work is being done, there is transfer of energy. Okay. Then other concepts you mentioned in IGCS include the SI units of work, which is actually the joule. The joule is the SI unit of work named after a physicist in the name of James Prescott Joule. And a joule, because work done is equal to force. Why do I use red? Because the work done is equal to force times distance in the direction of the force, and the force is measured in newtons, distance is measured in meters, we can define the unit joule as 1 Newton meter, or unit joule can be defined as the work done when a force of 1 Newton moves an object through a distance of 1 meter, that is a joule. A joule can be defined as the work done when a force of 1 Newton moves an object through a distance of 1 meter. Of course, this must happen in the direction of force. Work done when a force of 1 Newton moves an object through a distance of 1 meter in the direction of the force. That is the joule. Of course, if you're not good at writing long answers, you can just write a joule from its derived unit. You can define a joule as 1 Newton meter. 1 joule can be defined as 1 Newton meter. Just from because it's force times distance in the direction of the force, or force times displacement in the direction of the force. So we just multiply a Newton times a meter. Of course, as you advance in this level, you'll use larger units than the meter. So units will be expressed with the prefixes such as the kilojoule, and I think commonly the megajoule could also be used many times. Of course, we know what a kilo stands for. 1 kilo is 10 to the power 3, and we know what mega stands for. 1 megajoule is going to be 1 million joules. So many times work will be expressed in kilojoules or megajoules. That, I think, that is not something very new. You did the same in IGCSE. So on this slide, we have defined the unit for work as the joule. And since work is energy in transit, it means the same unit will be used for energy. We express this unit, I think, in base as SI base units. So if work done is equal to the force times distance in the direction of the force, and we know that force can also be given by mass times acceleration, so it means the SI base units of force will be those of mass, which is kilograms, and those of acceleration, which is meters per second squared. The base units of distance are meters, so it means the base units of work can also be force, which is kilogram meters per second squared times the base units of distance or displacement, which is meters. So the base units of work are going to be kilogram meters squared per second squared. So when you become an expert, this becomes an easy unit. It becomes part of you that in multiple choice questions, you don't need to even think about it. So the joule, the examiner will tell you to express a joule in SI base units. So 1 joule in SI base units is the same as kilogram meters per second squared. So in a nutshell, I'm saying we can write 1 joule as 1 Newton meter. We can write this as 1 kilogram meter squared per second squared. That is a joule. Okay, so that is work. A few things we need to note again. Work is also said to be done, or work is also done in moving against an opposing force, such as gravity or friction, any other form of resistance, such as friction or air resistance to the motion of the force. Unfortunately, in this case, the force acts in the opposite direction to motion, so we say work is done against. If you lift an object, for example, above the ground, for example, if you lift an object, or when a crane is lifting a heavy load, that is, work is done against the force of gravity. Or when a person lifts a load to a given height, the object is moving, but the force acting on the object, the force of gravity is acting downwards. So it's like, of course, there's lifting force. The lifting force may be doing the work vertically upwards, but it is doing work against another force which is acting vertically downwards. So work is also done in moving against some opposing force. The opposing forces could include friction, they could include gravity, they could include air resistance, because these ones always act in opposite directions to motion. If you are hitting a nail, for example, when a nail is being driven into a wooden block, maybe using a hammer, work is done against the resistance of the wood. You're trying to push the nail deeper into the wood by hammering, but there's friction between the wood and the nail. So work is done against this friction. So although we have said work is force times displacement, which is a product of two vectors, we are saying work is actually a scalar quantity. Work is not a vector quantity. At this level, by the time you reach this level, you know the six common scalars from AS physics. These include in the kinematics, the six vectors from AS physics. From kinematics, you have acceleration, displacement, and velocity. Those are three. In force, density, and pressure, you have force. Those are four. You have moments. Those are five. And the last vector quantity to talk about in AS is momentum. So if you know all those six vectors, then the rest are scalars. You have velocity, displacement, acceleration, force, moment, and momentum. Those are the vectors we talk about in AS, and the rest are scalars. So work is another scalar quantity. Even though it is a product of two vectors, after all, mathematically we know that a product of two vectors is actually a scalar quantity. Therefore, work is a scalar quantity. Example. Calculate work done by an engine which exerts a force of 9,000 newtons over a distance of 6 meters. I always don't calculate these questions because they are for IGCSE. But since these are just tutorials, since I don't teach this in class, my students can always refer to this. So work done is equal to the force times displacement. So that is 9,000 times 6 meters. This is 9,000 Newton meters. Newtons times 6,000 meters. 9 times 6, I think that is 54,000 Newton meters, which is the same as 54 kilojoules, because a Newton meter is the same as a joule, and 54,000 is the same as 54 kilojoules. A man lifts a box of mass 3 kilograms vertically upwards through 2 meters. If the gravitational field strength is 10, I don't want to use 10 at this level. We are now old enough to use 9.81 meters per second squared. Calculate the work done by the man in lifting the box. So we want to find the work done. So we know that work done is equal to the force times the displacement or distance in the direction of the force. When I write S, some students may think I'm writing speed, but this is displacement. The force is going to be the weight because we are doing work against gravity, so this is going to be the weight, then times the displacement. Sorry, I don't want to use W for weight since it has already been used for work. So the weight is mg, then times the displacement. So the work done here is going to be 3 kilograms times 9.81, then times the distance or the displacement, which is 2. I'll check with my calculator. 3 times 9.81 times 2. So this is approximately 59. So the work done there is approximately 59 joules. Okay. So even though work is a scalar quantity, it can be positive or sometimes negative. Now the positive and negative signs here do not mean that the work done it has direction. When we use positive and negative in vectors, we are referring to direction. However, positive work done on an object increases, we expect it to increase kinetic energy. For example, if the force is in the same direction as the displacement, we can think about the work done as being positive because it's going to increase the speed. It is going to increase the kinetic energy. However, negative work done decreases its kinetic energy. If work is done against a friction, it means the work done is going to decrease the kinetic energy of the object. So the work done against friction can be considered to be negative because it's going to decrease the speed. It is going to decelerate a moving object. And of course, zero work done means that zero work done means kinetic energy remains constant. So if there's no work done, then the kinetic energy is expected not to change because um, the force is not causing a change in speed in that case. That is what we mean by work done. Okay, so most of these concepts you must have mentioned them in IGCSE, and my role here is just to remind you of the concepts. They are almost the same concepts, we just slightly deviate from what we did in IGCSE. Let's talk about a special case which you may not have mentioned in IGCSE. That could be work done by an expanding gas. The work done by an expanding gas, you'll also see this in paper 4 in a unit called, I think that is ideal gases or temperature and thermodynamics. So this is now going to be a special case. We are going to consider a gas contained in a cylinder, for example, by means of a frictionless piston, as shown below. And suppose the pressure P of the gas in the cylinder is equal to the atmospheric pressure outside the cylinder. This is what we are talking about. You have a cylinder where this is a piston, for example, and a force is applied onto the piston. So you have a cylinder containing a gas, and the gas is held in the cylinder by a frictionless piston. That means there's no friction between the piston and the wall of the cylinder. And let's say the cross-sectional area of this piston is A. The cross-sectional area is A. Suppose the pressure P of the gas in the cylinder is equal to the atmospheric pressure outside the cylinder. So if the pressure of the gas is higher, it is going to push the cylinder until a point where the pressure of the gas inside the cylinder is equal to the external pressure or the atmospheric pressure outside the cylinder. So it means the force of the force exerted on the piston uh, by the gas is going to be the same as the external force outside. Therefore, we know that by definition of pressure as force acting normally per unit area, then it means the pressure is going to be the force over area. So, which means that the force of the gas is the pressure times the area when I make F the subject. And when the gas expands at a constant pressure, the piston moves outwards through a distance delta x. So the piston has moved through a distance delta x when the gas expands to reach an external pressure or to reach the atmospheric pressure. And the work done by the force exerted on the piston by the gas is going to be the force times the distance through which the piston has moved. Therefore, it means that the work done is going to be the force, which is pressure times area, times the distance through which the piston has moved. So when we just factor out, or when we just rearrange this would be P times A times delta X. And remember, cross-sectional area times delta X. So we have the cross-sectional area of the piston times another length. This gives us the volume, or the volume change. Therefore, we simply say that the work done is equal to the pressure times the change in volume. So the work done by an expanding gas is equal to pressure times change in volume, where the change in volume, or delta V, is the change in volume of the gas, and it should be measured in meters. That is the final volume minus the initial volume. So that is the work done by an expanding gas. So this is the only thing you never mentioned in IGCSE, that the work done by an expanding gas is the pressure times the change in volume. Of course, it also implies that there is a possibility of the piston being pushed inwards so that instead the volume decreases. So still work done will be given as pressure times change in volume. Okay, let's do a few quick trial examples. Question number 1, a baby of mass 5 kilograms is lifted up through a distance of 2 meters. What is the work done? So these are easy questions. I'll just try to give a hint very fast. Mass 5 kilograms, distance 2 meters. The work done is equal to force times distance in the direction of the force. So the force is the weight, so that is 5 times g, which is 9.81. That is the force. Then times 2 meters. So that gives us the work done. 5 times 9.81 times 2. So this gives us 98.1 joules. Find how much work is done when a force of 25 newtons displaces an object through a distance through 10 meters in the direction of the force. So here I will just press the answer. Work done is going to be 250 joules. Calculate the distance through which the object moves if a work of 250 joules is done when a force of 10 newtons is applied on the object. So they have given us the work done and have given us the force. So we just make the distance the subject. So the distance S is going to be 250 divided by 10, which is 25 meters. How much work is done on a vacuum cleaner pulled 6 meters by a force of 100 newtons at an angle of 60 degrees above the horizontal? So in this case, we have to resolve. The angle. Remember, the force must be in the same direction as the force. So because the force is acting at an angle of 60 degrees to the horizontal, when I resolve 100 newtons to the horizontal to be 100 cos of 60, therefore the work done is going to be 100 cos of 60, that is the force, then times the distance, which is 6. So 100 cos of 60 is, I think, 50, then times 6. So the work done is going to be 300 joules. Because this is at an angle of 60, how much work is done when 2 liters of water are raised vertically through 4 meters at a place where G is 10 meters per second squared? The density of water is 1 gram per centimeter cubed. So here we have been given a volume and we've been given the vertical height. This question is just, they have even given us the density, so they're just trying to tempt us to find the mass, just using density, the concepts of density. So the mass is equal to density times volume. So the density is 1 gram per centimeter cubed. The volume is 2 liters and 1 liter is 1,000 centimeters cubed. So there are 2 liters, so I will say 2,000. The volume is going to be 2,000 centimeters cubed. So centimeters cubed cancel, so the mass is 2 grams, 2,000 grams, which is the same as 2 kilograms. So the mass is 2 kilograms, and we have to find the force. The force is the same as the weight, which is going to be m times g. The force is going to be 2 times 9.81, that is the force. So now I want to find the work done, therefore I would simply say work done is equal to the force, which is 2 times 9.81, then times the distance, which is 4 meters. So I have 8 times 9.81, so this is 78 joules. You can also verify. A body of mass 10 kilograms is pulled a distance of 20 meters across a horizontal surface against a resistance totaling to 40 newtons. If the body moves with a uniform velocity, find the work done against the resistance. So since the resistance is totaling to 40, then the work done against the resistance is going to be the resistance force times the distance. So that is 800 joules. Okay. So I have given a self-check just to remind you of IGCSE concepts. A man pulls a box using a string. You can pause the video and try to solve this. Just remind yourselves about IGCSE concepts. A man pulls a box using a string attached to the box, making an angle of 30 degrees. with the horizontal. If the tension in the string is 10 newtons and the box moves through a horizontal distance of 10 meters, capture the work done by the man. Remember, in this case, I said you have to resolve either the force in the direction of the displacement, or you resolve the displacement in the direction of the force. So the force is acting at an angle to the horizontal. So the tension is the force, which is 10 newtons, acting on the object at an angle of 30 degrees. And then they say the distance here is 10 meters. So we have to resolve the force in the direction of the displacement. So it means the work done is simply going to be equal to 10 cos of 30, that is the force, then times 10. So I'll say 100 cos of 30, that is 87. A man pushes a box of mass 5 kilograms with a force of 2 newtons along a horizontal frictionless surface. The box is moved through a distance of 3 meters. Calculate the work done on the box by the pushing force. So a man pushes a box of mass that with the force of 2 newtons. So the pushing force is 2 newtons, the distance 3 meters. So I think that is direct. The normal contact force. Remember the normal contact force, if this is the box, the normal contact force acts vertically upwards at right angles to the surface. So the normal contact force has no effect on the object because it acts perpendicular to the direction of the displacement. The displacement is in this direction, the normal contact force acts upwards, so it has no effect on the displacement. So it means the work done by the contact force is zero. Then the weight, of course, also the weight acts vertically downwards, so the work done is also zero. A block is pulled along a rough horizontal surface. So rough means there is friction by a rope pointing at 60 degrees above the horizontal. The tension in the rope is 10 newtons and the frictional force is 5 newtons. The block moves a distance of 2 meters along the surface. Calculate the work done on the box by the tension. Of course, the work done by the tension we have to resolve. Let me draw the diagram. Where should I draw the diagram? Let me draw it here. So there is tension in the rope, which is 10 newtons, and then there is friction. There is friction between the object and the surface, which is 5 newtons. So the block moves a distance of 2 meters along the surface. So let's say the block moves in this direction, a distance of 2 meters. So it means the work done against friction is going to be frictional force times the distance, which is 2 meters. Then the work done by the tension, we have to resolve T in the direction of the displacement. So this angle is 60. So the first equation work done is going to be equal to the force, which is 10 newtons, cos of 60 times the perpendicular times the displacement, which is 2. So cos 60 is a half. So this is going to be 10 joules. Then the work done against friction is going to be the frictional force. Because the frictional force is acting parallel to the displacement, so we don't need to resolve anything. So that will be simply 5 newtons times 2, which is equal to 10 joules. Okay, so I've given you a hint on the self-check, but remember, for more practice, you would rather watch the solved past paper questions. As a teacher, I don't expect you to waste teaching students work, the concepts of work. They can just watch the video and then they do this past paper questions, which are the most important questions. I think that's the end of work. Let's also talk about power. Oh, there's still more self-check. Wow. How much work is done by a person who uses a force of 27.5 newtons to move a trolley 12.3 meters. So this is force, this is displacement. You just multiply or not, you can check the answer. High pressure gas in a spray can has a volume of 250 centimeters cubed. The gas escapes into the atmosphere through a nozzle so that the final volume is 4 times the volume of the can. So it means the final volume, I'll call it V2, is 4 times 250, which I think is going to be 1000 centimeters cubed. Calculate the work done by the gas, given that atmospheric pressure is 1.0 times 10 to the power of 5 pascals. So we have said that work done by an expanding gas is pressure times change in volume, which is going to be the pressure 1.0 times 10 to the power of 5, then times change in volume. Now here, this is where there is comment. The volume is in centimeters cubed. The pressure is in pascals. So we must change the volume from centimeters cubed to meters cubed. If 1 meter is equal to 100 centimeters, so it means 1 meter cubed should be 100 centimeters but raised to the power of 3, which becomes 1 times 10 to the power of 6 centimeters cubed. So 1 meter cubed is 1 times 10 to the power of 6 centimeters cubed. So that means 1 centimeter cubed should be equal to 1 times 10 to the power of negative. Now it becomes 1 divided by, so it's power minus 6 meters cubed. So this will be now, the change in volume is 1000 minus 250. So I will multiply this by 10 to the power of minus 6 to change it to meters cubed. So this is going to be 1000 minus 250 times 1 exponent 5. Then times 1 exponent minus 6. So this gives us 75 joules. So that will be the work done. Just note how I converted the volume from centimeters cubed to meters cubed. That is very important. A gas has a volume of 600 centimeters cubed. The gas expands at a constant pressure of 1.4 times 10 to the power of 5 pascals, so that its volume becomes 900 centimeters cubed. Calculate the work done by the gas during the expansion. So work done is equal to pressure times change in volume. So the pressure is 1.4 times 10 to the power of 5. Then times change in volume. Volume changes from 600 to 900, so it is 900 minus 600. But this should be times 10 to the power of minus 6 to change it to meters cubed. So this gives us 1.4 exponent 5 times 300 exponent minus 6. So this gives us 42 joules. A gas in a cylinder is kept at a constant pressure of 1.1 times 10 to the power of 5 pascals. The gas is heated and expands by 25 centimeters cubed. So this is the change in volume. Calculate the work done by the gas. So the work done by the gas is equal to pressure times change in volume. The pressure is 1.1 times 10 to the power of 5. Then the change in volume is going to be 25, but this should be changed to meters cubed. So times 10 to the power of minus 6. So the work done here is going to be 1.1 exponent 5 times 25 exponent minus 6. So this gives us 2.75 joules. You can verify. Okay, I think that is enough for work. We should now explore power. I think that's enough for work. Remember, I said this is one of the hardest units. If you want to know that it's not a direct unit, please visit the solved past paper questions because they give you a better picture of what really the examiner is looking for in a unit called work, energy, and power. Let's talk about power. So what do we mean by power? I think power is also a component you mentioned in IGCSE and or a concept you mentioned in IGCSE, and it's very, very easy. We said, or we normally say that someone is very powerful. That is, if he can do a given amount of work in the shortest time possible. So it's like there is a relationship between power and how quickly work is done. And how quickly work is done is equivalent to say to comparing work with time taken. So we can talk about power as the rate at which work is being done, or power is actually the work done per unit time. That is power. So we can define power precisely as the rate of doing work. That is, when I talk about rate, you can't say rate of doing work per unit time. That becomes wrong. It is a repetition of, because rate means something with respect to time. So power is the rate of doing work. Or I can say the work done per unit time. There I have not put the word rate. When I say per unit time, I don't include the word rate. Or I can say power is the rate at which the rate of performing work. Since we said work is energy in transit, we can also say power is the rate of transfer of energy or the rate of transferring energy. In simple terms, power is a measure of how quickly work is being done. So we can put all these definitions in formula so that in calculation we know that power can be defined or written as energy transferred over time taken, that is the rate of transfer of energy. Or we can say power is the work done per unit time, that is work done divided by time taken. Note that work done, we have said work done is force times displacement. And power will therefore be force times displacement. However, remember displacement over time is actually velocity. So in that case, therefore, we say that power can be force times velocity. So this is one of the only thing you never mention in IGCSE. The examiner will ask you to, from the definition of power, to derive power equals to F times V. So we have said power is the work done per unit time, and work done is force times displacement. So this becomes force times displacement over time. When we separate this to be force times displacement divided by t, and displacement over time can be the velocity, therefore we say power is equal to force times velocity. So power is equal to, or power can be obtained from force times velocity. That is the only thing I think you never mention in IGCSE, power being equal to force times velocity. Okay, then the SI units for power. I think the SI units for power that you mentioned in IGCSE is the watt, named in honor of James Watt, the scientist who was so much interested in the concepts of power and relating it to work done. And because we say the power is equal to work done over time taken, and work done is in joules and time is in seconds, it's like 1 watt is the same as 1 joule divided by 1 second. So we can define the joule as, the work done as joule per second. So the watt or the unit watt can be defined as the rate of doing work at 1 joule per second. Or simply in an exam, you can define a watt as 1 joule per second. We can also write this in SI base units, of course. We can write that in SI base units. 1 joule, 1 watt is the same as 1 joule over 1 second. Of course, the second is SI base units. But remember, we have already established the units of work in SI base units. So it means the units 1 joule is the same as 1 kilogram meters squared per second squared. So it means 1 watt is the same as 1 kilogram meter squared per second squared divided by second squared. It becomes kilogram meter squared per second cubed. So the watt in base units is kilogram meters squared per second cubed. Or we divide the base units of work by S so that we get S power minus 3. Many times we shall talk about large quantities or large values of work, I mean power. Therefore, large units may be very important, such as we shall be talking about the kilowatt, and we shall also talk about the megawatt. We know that kilo stands for 1,000, mega stands for 1 million, and so on and so forth. So those are the large units we expect to find or to use many times when we are talking about power. And just like work, because power is work done per unit time, if work is a scalar and time is a scalar, automatically two scalars still give a scalar. So power is a scalar quantity, it is not a vector quantity. I said there are only 6 vector quantities you talk about in this AS level. After those 6 vectors, velocity, displacement, acceleration, force, moment, and momentum, the rest are going to be scalars. So that is power. Okay, so let's talk about a few examples because there is nothing much to talk about under power. Let's talk about a few examples of power under power. Calculate, these are similar examples to the ones we mentioned in IGCSE. Calculate the power of a water pump which can fill a water tank 10 meters with a height of 10 meters height with 3,000 kilograms of water in 20 seconds. So the most important thing is to find the work done. And if we know the work done, then we can find the power. So power in this case is going to be equal to work done divided by time taken. The work done is going to be force times displacement divided by the time taken. The force, we have mass, so the force is going to be the weight. So this is going to be mg, which is the weight, times displacement divided by time taken. Now I will just substitute 3,000 times 9.81, then times displacement, which is 10 meters, divided by 20. I can check my calculator. 3,000 times 9.81 times 10 divided by 20. So I think this is correct to two significant figures. I'm getting 14715 watts or joules per second. A man lifts a box of 10 kilograms through a vertical distance of 2 meters in 4 seconds. Calculate the power he developed. So here I will just quote from somewhere there. And I will say power is going to be the force, which force is mg, 10 times 9.81 times the distance, which is 2 meters, divided by the time, which is 4 seconds. And I think that answer is correct. A boy of mass 60 kilograms runs up a flight of 60 steps in 10 seconds. If the height of each step is 20 centimeters, calculate the power he developed. So total distance is going to be 60 steps times 20, which is 1,000, I think, 200 centimeters, which I think is going to be 12 meters. So that is the distance. So we want to find the power. Power is equal to the work done divided by the time taken. So the work done is going to be the force, then times the distance divided by the time. The force is mg times the distance divided by the time. M is 60, G is 9.81, and then the distance is 12 meters divided by the time, which is 10 seconds. So that is 60 times 9.81 times 12, then divide by 10. 60 times 9.81 times 12 divided by 10. So this is giving me 7 706.32, which is approximately 710 watts. So I think this one used a different value for G, but that should be 710. Okay, so that is the power. Let me check part B. 10 times 9.81 times 2 divided by 4. Yeah, this is 49 watts. It's always not advisable um, to write these to less than two significant figures. Try example 2. A car of mass 750 kilograms starts from rest on a level road and is uniformly accelerated for 10 seconds until its speed is 18 kilometers per hour. If the resistance to motion is 49 newtons, find the power of the car 10 seconds after the start. So want to find the power of the car. It starts from rest on a level road and is uniformly accelerated for 10 seconds until its speed is 18 kilometers per hour. If the resistance to motion is 49 newtons, find the power of the car after the start. So if the resistance is if it is moving, if it is accelerated for 10 seconds until its speed is 18 kilometers per hour, it means the acceleration is constant, which means the resultant force is also constant. So first of all, 18 kilometers per hour, I think this is 18 kilometers per hour is 5 meters per second. That's number one. So the car is accelerated for 10 seconds and its speed is that. So one, we are going to first find the resultant force. The resultant force is given by mass times acceleration. The mass is 750 and the acceleration is final velocity, which is 5. It started from rest, so minus 0, divided by t, which is 10. Change in velocity over time, that is the acceleration. So the resultant force is going to be 750 times 5 over 10, which is 375 newtons. Remember, the resultant force is given by the driving force minus the frictional force. So it means that the total force which is driving the car is the driving force. So Fd is going to be the resultant force, which is 375, plus the friction, which is 49. And I think this gives us 375 plus 49, 424. So this is the force responsible for moving the car. One, it should accelerate it, and two, it should overcome the resistive force. And if it remains constant after that, then we can use power is equal to force times velocity. So power equals to force times velocity. So the driving force is 424. This is driving force, total force moving the car. 424 times the velocity, which is 18 kilometers per hour, which is 5. And I think this gives us 2120 watts. You can also check that. A train of mass 500 tons, that is 500,000 kilograms, because 1 ton is 1,000 kilograms, has a maximum speed of 90 kilometers per hour. What is 90 kilometers per hour? That is 90 times 1,000 divided by 3,600. So this one is the same as 25 meters per second. While moving up an incline of sine 1 over 5, So, sorry, sine inverse of 1 over 5. What is sine inverse of 1 over 5? 1 divided by 5 is 0.2. It's about 11 point something. Against frictionless resistance of 100,000 newtons, find the maximum power of the engine. So, a train of mass 500,000 kilograms has maximum speed of 25 meters per second while moving up an incline of sine inverse of 1 over 5 against a frictional resistance of 100,000 newtons. Find the maximum power. Okay, I really don't find space, but I must draw this. I must sketch this somewhere to give you a hint. So because there's an incline, I'll sketch the incline here. Let this angle be theta, which is sine inverse of 1 over 5. And then there is a car. I'll just do a free body diagram like that. And it has a maximum speed of 90 kilometers. If this is the maximum speed while moving, it means the acceleration is 0. It has reached the maximum speed, so the acceleration is 0. So the resultant force must be 0. So the force upwards must be equal to the force downwards. And the force downwards, we have the weight of this mg. This has a component down the plane, which is mg sine of theta. And it also has the friction acting downwards. So there's also friction. So there are two forces acting downwards, mg sine theta and friction. And those forces must balance with the force upwards, which I'm going to call Fd. So Fd, the force upwards, should be equal to mg sine theta plus the frictional force downwards. Because we reach maximum speed, it means the acceleration is 0. So at that point, it means the resultant force is 0. So the forces in opposite directions must be equal and cancelling out. Remember, this was 25 meters per second. So all I need to find is the force Fd. So Fd is going to be equal to m, which is 500,000 times g, which is 9.1. If sine inverse of theta is if theta equals to the sine inverse of 1 over 5, so it means sine theta is 1 over 5. So I'll just say times 1 over 5. Then plus the frictional force, which is 100,000. So I have 500,000 times 9.81 divided by 5 plus 100,000. So the driving force is equal to 108,1000 newtons. Then if I want to find the maximum power, so the maximum power is going to be equal to, so this is power is force times velocity. So this is going to be equal to 108,1000 times velocity, which is 25. I don't think this is correct. That is wrong. So that is 108,1000 1000 times 25. So this is 2702500 watts. This is wrong. So this is going to be the power. You first remember when we reach maximum speed, it means the acceleration is zero. And when acceleration is zero, it means the resultant force is also the force moving the train upwards from the engine must be equal to total forces downwards. That's why I got mg sine theta plus the frictional force. If you're doing math, you are going to get used to such problems in mechanics. A truck of mass 1,500 kilograms moves with a uniform velocity of 5 meters per second up a straight track, inclined at an angle of 30 degrees to the horizontal. The total frictional resistance to the motion of the truck is 580 newtons. Actually, the power developed by the engine. Since the velocity is uniform, total forces up the truck, up the plane, should be equal to total forces down the plane. And the forces down the plane, we have already seen that from the previous example, is the driving force from the engine. The driving force from the engine up the plane should be equal to the total forces down the plane, which is mg sine of theta plus the frictional force down the plane if it is going up the plane. So this is going to be equal to mg, which is 1500 times 9.81 sine of 30 plus the frictional force, which is 580. That is the driving force. So this is going to be the driving force, which is going to be equal to 1500 times 9.81 times sine of 30 plus 580. So this force is 5938 newtons. So the power developed is going to be equal to the force times the velocity, which is going to be 7938 times 5, which is equal to 3968, which is approximately, I think, the same as this. I think that is correct. If the engine of the truck in B above cannot develop a power greater than 75 kilowatts, because this is approximately 40 kilowatts, calculate the maximum speed attainable, the maximum speed greater attainable by the truck. Okay, whatever it is, whether it is greater attainable by the truck, if the power is 75 kilowatts, and they said if the engine of the truck in Roman 1 above cannot develop a power greater than this, so that means the driving forces remain the same. So we want to find the speed. So we just make V the subject. So V is going to be the power divided by the force, the driving force. So this is going to be 75,000 divided by the driving force, which is 7938. So 75,000 divided by 7938, which is 9.45 as required. So because this is the driving force, we just make V the subject, and that is the answer. Yeah, that is a good trial example. Time for self-check, I think. One student told me, teacher, stop doing self-check for us. Let's do it for ourselves. So you can always pause the video and use the solve the self-check. A dog of mass 30 kilograms runs up a flight of 120 steps in 40 seconds. Each step is 10 centimeters. Calculate the power. So total distance, you just get the number of steps times 10. This will be 1,200 in centimeters, which is 12 meters. You have time, you have mass. The mass gives you the force, which is equal to the weight, which is m times g. So you can find the power from work done over time taken. I think that is easy. Calculate the power of a car engine required to lift 10 power 5 kilograms of rice per hour. So time is 1 hour. So 1 hour is 3,600 seconds. So time is 3,600 seconds. Given that G is 9.81, so power is equal to work done over time taken. The work done is mass. The work done is force, which is 10 to the power 5 times G, which is 9.81. That is force. Then times distance, which is 100 meters, divide by the time, which is 1 hour. That is 3,600. So you get the answer in watts. A car uses 75 kilowatts of power and moves at a uniform speed of 100 kilometers per hour. What is the forward thrust caused by the engine? So we want to find the force. We just change the speed to meters per second. So you get 100 times 1000 divided by 3600. This one is 27.8 meters per second. So the force is equal to the power divided by the speed. So you get 75,000 divided by 27.8. I think that should give you the answer in newtons. How fast should 2,000 kilograms car move up 30-degree incline to do work against gravity at a steady rate of 200 kilowatts? So they have given us the work done as 200 kilowatts. I can sketch this for simplicity here. This incline is 30 degrees. Let me draw here a car like this. Its mass is, its weight is going to be 2000 times g, or times 9.81. So down the plane we have mg, sine of 30. So how fast should a 2000 kilogram car move up a 30-degree incline to do work against gravity at a steady rate of 2000 kilowatts per hour? So it means it should be moving at a constant speed. So the force upwards is equal to the force downwards. So it means if there is no friction, then we shall say the work done is equal to the force times the distance, or the s. The work done is 200,000. The force is going to be mg sine theta, which is going to be 2000 times 9.81 sine of 30, then times the distance. Oh, sorry, this is power, not work. To do work against gravity at a steady rate of that. So let me just use the expression for power, not the one for work. So power is force times velocity. So velocity is going to be equal to the power divided by the force. So the power is 200,000 divided by the force, which is, of course, we have seen the force is mg sine 30. So that is 2,000 times 9.81 sine of 30. So 200,000 divided by 2000 times 9.81 sine of 30. So the speed is going to be 20.4 meters per second. You can also verify. So here I may not be organized because I'm just giving you hints on these questions. A car of mass 750 kilograms starts on a rest. I think we have answered this one. And its speed is 18 kilometers per hour. We have answered this question. A small electric motor is used to lift a weight of 1.5 newtons through a vertical distance of 120 centimeters in 2.7 seconds. Calculate the useful power output of the motor. So they have given us the force, which is the weight. You just change the distance into meters and you use the time and check if this is correct. A board of mass 60 kilograms runs up a flight of steps in a time of 1.8 seconds. There are 22 steps and each one is of height 20 centimeters. Calculate the useful power developed in the boy's leg. So we have the mass, we can find the force or the weight, which is mg. Sorry, we can find the force, which is mg in this case. Then we just find the distance. Distance s is going to be 22 steps times 20, which is 440 centimeters, which is the same as 4.4 meters. That is the distance. So we just find power from work done over time taken, which is mg60 times 9.81, that is force. Distance is 4.4 meters. Divide by time, which is 1.8. I think that gives you the power. Okay. Self-check 3. The output power of the electric motor of a train is 3.6 megawatts when the train is traveling at 30 meters per second. Calculate the total force opposing the motion of the train. So this one you just consider power equals to force times velocity and you find the answer. Capture the electrical energy converted into thermal energy when an electric fire rated at 2.4 kilowatts is left switched on for a time of 3 minutes. So this is 3 times 60 to change it to seconds, 180 seconds. So we want the electrical energy. So remember, power is the energy transferred per unit time. So it means energy is going to be power times time. So you have the power and you have the time in seconds. The answer here will be dash in joules. The output power of the electrical motors of a train is 2.6 megawatts. Calculate that, when the train is traveling at 15 meters per second, calculate total force opposing the motion of the train. So here we just use power is equal to force times velocity. We have the power, we have the velocity, we just need the force. So that is the self-check. And I think let lesson 1 end there. Lesson 2 shall concentrate on energy. We have seen concepts of work and power. In lesson 2, let's concentrate on the concepts of energy. Until next time, bye bye.